Good day. Today we begin exploring one of the most crucial and frequently used topics in database management, the fundamentals of data retrieval using the select operator. This operator is fundamental for retrieving any information from a relational database. Our goal for today is to master the canonical structure of select queries, learn how to choose specific columns, filter rows based on simple and complex conditions, and sort and limit results. Understanding these concepts is essential for any data professional. Before diving into details, let's look at the structure of today's lecture. First, we will break down the canonical structure of the select operator and the functional purpose of each of its main clauses. Next, we will focus in detail on data filtering using the where clause, examining both standard and specialized operators for constructing flexible conditions. The third item on our agenda will be subqueries. We will learn how to use the results of one query to filter another. Finally, we will discuss aliases, which make our SQL code significantly cleaner and more understandable. So, let's start with the basics, the structure of the select query. Moving to the first point, the select operator is the heart of the query language. Its main task is not to change data, but merely to read it and form a new set based on it, a so-called result set. Each clause performs its unique function. Select defines which columns we want to see, from which table to retrieve them, where, which rows we are interested in, order by, in what order to display them, and limit how many rows to show. The minimally required construct is select and from. The rest are optional and used to refine the query. This is what the canonical query structure looks like. It is very important to remember this strict order of clauses. Violating this order will result in a syntax error. Square brackets, as always in documentation, denote optional parts. This means where, order by, and limit can be omitted. The keyword distinct is also optional, which we will discuss a bit later. To see the select operator in action, let's imagine we are working with a university database. We have a students table, whose schema is shown on the slide. It contains basic information about each student. This is what the query to solve our task looks like. In the select clause, we clearly list the columns we are interested in, last name and first name. This is an example of projection. We project data from the table onto a new, narrower set of columns. The from clause indicates that the data source is the students table. As a result of executing this query, the system will return a new temporary table containing only these two columns and absolutely all rows from the original students table. Now let's look at a special symbol that allows selecting all columns without listing them. There is a way to select all columns from a table without listing them. This is done using the asterisk symbol. At first glance, this is very convenient, especially when you just want to quickly review the contents of a table. However, I want to emphasize that using select asterisk in your application code, procedures, or views is a bad practice, a so-called anti-pattern. Why? Firstly, it makes your code fragile. Imagine a new column is added to the table. Your query will automatically start returning it, and the program, which expected, say, 5 columns, will receive 6, which can lead to errors. Secondly, it's inefficient. You load absolutely all data from the row from the database, even those you don't need for a specific operation. This creates unnecessary overhead. Therefore, the rule is, for manual analytics, asterisk can be used. For code, always explicitly list the necessary columns. This is what a query using the asterisk looks like. It's simple, concise, but as we've already established, potentially dangerous for use in final code. The result will be a complete copy of the student's table at the time the query is executed. Next, we will look at how to eliminate duplicates from our selection results using the distinct keyword. Often, a situation arises where we need a list of unique values, not a complete list of all values. For example, if we want to know which faculties actually have students, we don't need the faculty ID for every single student. We need a unique list of these IDs. By default, select will simply return a column where each faculty ID will be repeated as many times as there are students enrolled in it. Often, a situation arises where we need a list of unique values, not a complete list of all values. For example, if we want to know which faculties actually have students, we don't need the faculty ID for every single student. We need a Let's look at two queries. The first, without distinct, simply selects the faculty ID column. If there are 100 students in the table, it will return 100 values, many of which will be repeated. The second query does the same, but with the distinct keyword. The system will first, figuratively speaking, collect all 100 values, and then filter them, leaving only unique ones. As a result, we will get a short list of faculty identifiers, where at least one student is enrolled. An important point: distinct does not guarantee any particular sort order. The result will be unique, but unordered. For this, there is a separate clause, which we will discuss next. So far, we have selected either all rows from a table or all unique values. But most often, we only need a specific portion of the data that meets certain criteria. This is precisely why the where clause exists. It acts as a powerful filter. We specify a certain condition in it, which in database terminology is called a predicate. The system takes each row from the source table and checks it against this condition. If the condition is true, the row proceeds to the resulting selection. Otherwise, it is discarded. Thus, where allows us to move from selecting all data to selecting necessary data. Let's see what this looks like in practice. Let's look at a simple example. Our task is to get a list of students, but not all of them, only those who are studying at a faculty with identifier 1. We add the where clause after from and specify the condition, faculty ID equals 1. Now the DBMS, before returning the data to us, will check each row in the students table. If the value of the faculty ID column in a row is 1, this row will pass the filter, and we will see the student ID and last name of that student. All other rows where faculty ID is not equal to 1 will be ignored. This is the basis of filtering. Next, we will look at how to build more complex conditions. After we have filtered the rows we need using where, there is often a need to order them. For example, to display a list of students alphabetically or by academic performance rating. The order by clause is responsible for this. It's important to remember, if you don't use order by, the relational DBMS does not guarantee any specific order of returned rows. It can change from query to query. Therefore, to get a stable ordered result, always use order by. We can sort in ascending order, ASC, which is the default behavior, or in descending order, DSC. Let's look at an example. Let's consider a practical task. We need to create a student ranking, displaying those with the highest GPA first. For this, in the Order By clause, we specify the GPA column, and for the sorting to be in descending order, from highest to lowest, not ascending, we explicitly add the desk keyword. As a result of executing this query, we will get a list of last names and GPAs, where the first in the list will be the student with the highest GPA. If we had not specified desk or had specified ASC, the list would have started with the student with the lowest GPA. And the last clause in our basic structure is limit. It performs a very simple but extremely useful function. It truncates the result set to the specified number of rows. This is extremely important, for example, in web applications. When you browse a product catalog, you are shown 10-20 items per page, not all thousands at once. This is pagination, implemented using limit. The key point to remember: limit is applied at the end, after the data has been filtered and sorted. This allows us to get, for example, the top 10 best students, and not just the first 10 rows encountered in the table. It should also be noted that the syntax may differ in various DBMSs. For example, in MS SQL Server, top or offset fetch is used instead of limit. Let's combine the last two clauses to solve the task. Find the 10 students with the highest GPA. Look at the query execution logic. First, from students defines the source. Then, Order By GPA desk sorts all students in the table in descending order of GPA. And only after that, limit 10 takes the first 10 rows from this recently sorted list. Finally, select displays their last name and GPA. If we hadn't used Order By, limit 10 would have simply returned 10 arbitrary students. It is the combination of sorting and limiting that gives us a powerful tool for creating rankings. Now that we know how to specify a simple condition, let's make it more complex. The where class allows combining multiple conditions using the logical operators AND and OR. AND, logical AND, makes the filter stricter. Both conditions it combines must be true. OR, logical OR, makes the filter more flexible. It's enough for at least one of the conditions to be true. A very important point, often overlooked by beginners, is operator precedence. AND has higher precedence, similar to multiplication in mathematics. To ensure the correct order of condition evaluation, always enclose logical blocks in parentheses. Let's look at an example. Task: find all excellent students from faculties 1 and 3. Here we have two conditions. The first is belonging to one of two faculties. The second is a high GPA. See how we grouped the first condition in parentheses: faculty ID equals 1 or faculty ID equals 3. This ensures that the system first checks if the student is enrolled in one of these two faculties, and only if this complex condition turns out to be true, the system will check the second condition, connected by AND, GPA greater than or equals 4.8. If we hadn't used parentheses, the query would work incorrectly. Due to AND's precedence, the system would first find excellent students from faculty 3, and then add all students from faculty 1 to this result, regardless of their GPA. Therefore, using parentheses here is critically important for obtaining a correct result. In addition to basic operators, SQL offers several specialized constructs for typical filtering tasks. The first of these is between. This operator is syntactic sugar that allows checking whether a value falls within a specified range more elegantly and clearly. It's important to remember that both boundaries of the range are included in the check. That is, between 3 and 4 means greater than or equal to 3 and less than or equal to 4. Although the same result can be achieved using the AND operator, using between is considered better practice because it makes the query author's intent more obvious. On this slide, you see an example of finding students whose GPA is between 3.0 and 4.0. As you can see, the between notation is significantly more concise and easier to understand than its full equivalent, where GPA greater than or equal to 3.0 and GPA less than or equal to 4.0. The result will be absolutely identical. The next useful operator we will consider is in, which allows checking for the presence of a value in a list. The next operator, in, saves us from writing long and cumbersome constructs with many ors. Imagine you need to find students from 5, 10, 20 different faculties. A query with or would become very long and unreadable. The in operator allows you to pass a list of values in parentheses, and it will check if the value in the column is among the elements of that list. This makes the code not only shorter, but also much easier to understand and maintain. Look how elegantly the solution to the task Find Students from Faculties 2, 4, and 7 appears using the in operator. We simply specify where faculty ID in and list the faculty identifiers we are interested in within the parentheses. This syntax is completely equivalent to the construct where faculty ID equals 2 or faculty ID equals 4 or faculty ID equals 7, but you'll agree it's much cleaner and more understandable. Next, we will look at how to search for data by text patterns using the like operator. Very often, we have to work with text where we don't know the exact value, but only a part of it. For example, to find everyone whose last name ends with a specific sequence of letters. For such tasks, the operator like exists. It works with two simple but powerful wildcards. The percent sign means anything of any length, including an empty string, and the underscore is a strict placeholder for exactly one character. Understanding the difference between them is key to correctly creating patterns. Look at the first example. The pattern %enco means we don't care what comes at the beginning of the last name, indicated by the % sign. The main thing is that it ends with enco. The second example is more specific. The pattern O__G means the first character must be O, followed by exactly 2 of any characters, indicated by the 2 underscores, and the last character is G. Thus, this pattern will find names like Oleg, but not Ostap or Own. The next important topic is how to work with missing data, that is, with null values. One of the most difficult aspects of SQL for beginners to understand is the concept of null. It is important to realize that null is not a value in the usual sense. It is a marker of unknowingness. We don't know what's there, whether it's 0, some number, or simply data that hasn't been entered yet. Due to this unknowingness, any direct comparison with null, for example, GPA equals null, will yield not true or false, but a third logical result, unknown. And the where clause discards all roles for which the condition is not clearly true. Therefore, remember the golden rule. For checking for the presence or absence of data, always use is null and is not null. This is the only correct way. Here's a practical example. Suppose we need to find all first-year students for whom the GPA has not yet been calculated, and the corresponding field in the database contains null. The query where GPA equals null would not return any rows, which would be logically incorrect. The correct query, which you see on the screen, uses the isNull operator. It will correctly find and display all students for whom the GPA field is not filled. We have completed the review of filtering operators. Now we move on to the next major block of our lecture, subqueries. We are moving to the third point of our plan, subqueries. Often for filtering, we need a value that is not a static constant, but rather must be retrieved from the database. For example, to find students whose GPA is higher than the university average, we first need to calculate that average GPA. Subqueries allow doing this within a single query. The key idea: one select operates inside another. First, the inner query is executed. Its result, which can be a single value or an entire list, is passed to the where condition of the outer query, which then completes its operation. Let's consider the most common case, when a subquery returns a list of values. This is the most common way to use subqueries. Imagine we need to find students from Faculty of Computer Science. But in the Students table, we only have the faculty ID, not its name. The name is stored in another table, Faculties. This is where a subquery comes in handy. The inner query will go to the Faculties table, find the required ID by name, and return it. And the outer query will take this ID and use it to filter students. Thus, we link data from two tables without knowing the specific ID beforehand. This is what the complete query looks like. The DBMS will first execute the inner part within the parentheses. It will query the faculties table and find the faculty ID corresponding to the name Fakultet Kompjuternych Nauk. Suppose this ID is 3. After that, the subquery result is substituted into the outer query and it transforms into the already familiar construct, where faculty ID in 3. Thus, the query becomes dynamic. We don't need to hard-code the faculty ID, the system finds it itself. Note the double apostrophe in the faculty name. This is the standard way to escape a single apostrophe within a string in SQL. Another common type of subqueries are those that return a single value. For example, if we need to calculate the average GPA for the entire university, the result of this calculation is a single number. Such scalar results can be used in the where clause for direct comparison. That is, we can find all students whose grade, for example, is higher than this recently calculated average. This is a very powerful tool for comparative analysis. Here's an excellent example. Task: find all students who perform better than the average student. Again, the DBMS first executes the inner query, select AVG GPA from students. It will iterate through the entire table, calculate the arithmetic mean of all values in the GPA column, and return a single number, for example, 4.21. Then this value is substituted into the outer query, and it takes the form where GPA greater than 4.21. After that, the system finds all students who meet this condition. While subqueries are an extremely powerful tool, it's worth remembering that they can be resource-intensive. Often there are alternative, more efficient ways to achieve the same result, for example using join, which we will cover in the next topic. And finally, let's talk about pseudonyms or aliases. It's a very simple concept. We give a temporary, more convenient name to a column or table directly within our query. Why is this necessary? Firstly, for readability. Instead of technical column names, we can give them understandable names for reports. Secondly, for brevity. Instead of a long table name, you can use a single letter. Most importantly, it's absolutely safe. An alias only lives as long as one specific query is being executed and does not affect the structure of the database itself. Let's see how this works for columns. Let's start with column aliases. Their main goal is to make the result of your query more understandable. For example, instead of the technical name last name, we can display a column with the name last name. This is especially useful when a column does not exist in the table, but is the result of some calculations. For example, we calculate the GPA on 100-point scale. The syntax is very simple. After the column name or expression, we write AS and the new alias. Although AS can often be omitted, its use makes the code more explicit and readable, so I advise always writing it. If your alias consists of multiple words, remember to enclose it in double quotes. In this example, we do three things. The last name column in the result will be called last name. The first name column, first name. We create a new virtual column by multiplying GPA by 20 and give it the understandable name GPA 100. As a result, we will get a table with three columns: last name, first name, and GPA 100. This is much more informative for a person who will be viewing this report. Now, let's consider how and why to give aliases to entire tables. It might seem strange to give alias to a table when there's only one in the query, but this is one of those useful habits I strongly recommend developing. The true power of table aliases is revealed when we start joining data from 2, 3, or more tables. Imagine that in the students table and in the faculties table there is a name column. How will the system understand which specific name you want to select? Aliases solve this problem elegantly, allowing you to write, for example, s.name and f.name. This makes your code unambiguous and clean. Let's look at the syntax. In this simple example, we gave the students table a short alias s directly in the from clause. Now, throughout the query, we can refer to its columns using the prefix s dot, for example, s.lastname. Although it doesn't offer significant advantages here, the habit of using aliases for tables is crucial for writing professional and scalable SQL code. This concludes the main material of our lecture today. Now, to consolidate our knowledge, let's consider a few questions. With this, our lecture is concluded. We have covered the fundamental select operator, learned to select and sort data, filter it using simple and complex conditions, and use subqueries and aliases to create flexible and readable queries. Thank you for your attention.